Here's a question from the referred exam for 2019, and it's concerned with rotation and translation of points. It's asking us to first rotate a point P1 around the y-axis by 60 degrees and then translate it by 1 unit in the x, minus 1 in the y, and 2 in the z, leading to a new point in frame A called P2. So it first of all wants us to write down the rotation matrix, which achieves a 60-degree rotation around the y-axis. So what we have to do is go and find the right appropriate rotation matrix, which you can look up in the table of formulas, and that would normally be in the back of the exam book, but if you've got, obviously you can look it up for your notes as well, and that will be given by this formula here. The important thing to notice is we can tell this is around the y-axis because it's unaffecting points in y. We can immediately see that. Now 60 degrees is one of those angles which gives some quite clean results, so you can either work it out using a calculator, but you might even know off by hand 60 degrees, the cosine of that is 0.5 and the sine is 0.8660. So we can plug those values in, so the cosine goes to 0.5, sine goes to 0.8660. Obviously it goes to larger numbers of decimal places as well, but we don't have to worry about more than about 4 decimal places. That's plenty for us. And obviously I've also, as you can see here, I've used MATLAB, so I'm less likely to make mistakes when I'm actually showing you the results of these things. So that gives us our rotation matrix as requested. Now it wants us to do something also quite simple. It wants us to write down the corresponding homogeneous rotation matrix. Right. So the rotation matrix is just 3 by 3, and we have to write down the homogeneous rotation matrix. And as we know, homogeneous rotation, well, the homogeneous matrix is composed of the rotation component, which is the 3 by 3 part, which is on the left at the top, right? So that's our rotation matrix. It's composed of no translation here, so 0, 0, 0, and the last row is 0, 0, 0, 1 always. And if we're going to be multiplying with points, we have to always take our position vector and add a 1 on, and when we actually get the result from transforming something, we'll end up with a 1 on the result as well. So we put in the values then, we did that previously, of cos 60 degrees and sine 60 degrees, and we end up with the homogeneous rotation matrix. Again, you can see the zeros for translation and the 3 by 3 rotation matrix here. So write down the homogeneous translation matrix that achieves a translation of 1 in x, minus 1 in y, and 2 in z. Right, so in other words, let's jump straight to the homogeneous transformation matrix. We know that a translation matrix then has no rotational components, so the rotational part of the homogeneous transformation is going to be the identity matrix 1, 1, 1. And we have the translation in x, y, and z, which in this case we were asked to put in 1 in x, minus 1 in y, and 2 in z. Right, so you just have to substitute those values in, and we come up with our homogeneous transformation matrix. Now calculate the single homogeneous transformation matrix that realizes required rotation and translation. And we do rotation first and then translation, right? So in this case, we're multiplying the rotation matrix on the right with the translation matrix on the left. You can actually, if you want to, you could just say, well, this is, doing the rotation followed by translation is exactly what the homogeneous transformation does anyway, so you can directly type in basically the translation part in the rotation matrix, and it will do that without actually having to do the multiplication yourselves. Now we can actually use it to actually transform a point. We're given a point 1, 1, 1. What is the transformed point under this transformation that we've just calculated? Obviously what we have to do, first of all, we have to make it into a homogeneous point by adding a 1 on the end. Then we're going to have to calculate the new point by calculating the homogeneous transformation multiplied by our homogeneous point. So it's going to be point on the right multiplied by transformation matrix on the left, and that's going to give us a simple value, which you'd probably want to do with a calculator, of our transformed point.